In this video, we'll be doing our first exploration into power series and functions. So by definition, a power series centered at x equals 0, so you need that whole expression, you need to state that it's a power series and also state its center, is a series of the form c sub n times x to the power of n. So we're dealing with polynomials. Okay, take a look. C sub 0, you'll have some formula for the constants. When you plug in n, you'll get numbers here for your c's, and then you'll have a polynomial, which means powers of x, specifically whole number powers on x. Let's say that our power series is centered away from 0 at some x equals a. Then your power series will still have that format of some constant times x minus a to the n, so that when you plug in n, you'll get numbers for your coefficient, and then you'll get x minus a raised to powers. So there's a time and place for each of these, and to start with, we're going to learn generally what they are, and then we'll learn how they're applied. So first we'll explore what are they, what are their properties, and then we'll kind of go over, okay, here's how we use them. So when do these series converge is a very interesting question and important to explore. So these power series can converge in 3 different cases, and case 3 kind of breaks up into some subcases, but it's all about, basically the endpoints. So case 1, a power series can converge only at its center. So its convergence would look like this. Picture here. Converges in green at just a, and then it is divergent for all other x values. So if I plug in any x that is not the center, it's divergent. Case number 2, your power series converges no matter what x value I plug in. Case number 3, the power series converges on some interval around the center, and we'll call that length of half the interval the radius, and we'll call it capital R, and your power series will be convergent when you plug in any x value within R units in either direction from the center. Now notice that the endpoints are possibly convergent, possibly not, and we have to check in every single instance manually. So what we will do is we will plug in the endpoints, x equals the endpoints, and we'll physically check it in each example. So here's all the cases for what that could look like. You could have your series converge on the interval that's interior but not on the endpoints. You could have your series converge on your interval and just one of the endpoints. Or you could have the series converge on the interval as well as the endpoints, but notice that it diverges outside of that interval for sure. So to find what the radius of convergence is, we're going to be applying our ratio tests, and then we'll check our endpoints individually. So that's going to be our strategy here. So here's our first concrete example of a power series. Our power series is x to the n over n factorial, and we're going to find the interval of convergence and radius of convergence. So starting off, we're going to take our limit as n goes to infinity of the absolute value of x to the n plus 1. This is our ratio test setup. N plus 1 factorial over x to the n over n factorial. Okay, now in this case, unlike with our previous study when we didn't have any x's, when we did our ratio test, sometimes we were able to get rid of the absolute value bars by simplifying some things out of the formula. And in this instance, we can't do that because as x varies, the absolute value bars may or may not need to be included. X can be any real number. So because x can be any real number, we don't really know if this is going to be positive or negative. So I have to leave my absolute value bars around my x terms is what I'm getting at. We can simplify that to being the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Still got the absolute value bars. And then this simplifies. Our factorials will simplify to give us an n plus 1 in the denominator. And our x to the n plus 1 over x to the n will simplify to just give us a single x. Okay, again, keeping that in the absolute value bars. And now we're going to remember that this has an n part and an x part. And the x part is independent of the limit. So I'm going to pull the absolute value of x out. And note that we're computing the limit as n goes to infinity of the absolute value of 1 over n plus 1. The absolute value bars, we don't really need them there because n is always positive. So this is equal to x times 0. Okay, so x times 0 gives me 0. And 0 is less than or equal to 1. So remember the ratio test that says if you get some finite limit that is less than 1, you have a absolutely convergent series. So remember that what we were trying to go for to get a convergent series was you're looking for a finite limit somewhere between 0 and 1. So we got 0, which is less than 1 for all x in the real numbers, which means regardless of what x we plug in, this limit will always be 0. So for all x in the reals, our power series is convergent. Okay, we don't have any endpoints to test because our interval convergence is negative infinity to infinity. So we say our radius is infinity and our interval of convergence is negative infinity to infinity. So that answers our question of what we're looking for. Okay, now we're not quite ready to get into this in full detail, but I'd like to preview where we're headed with this concept, which is that what these series converge to. When we first learned about series in our previous unit, we were just learning about series of numbers. And when they added to something, they added to a number. They converged to a numerical limit. These power series will not converge to a numerical limit. They will converge to what we call a function. So these are going to converge to some function f of x. And we don't know what those functions are yet, but in a future video, we'll cover how the functions specifically you can compute these series and vice versa. So this one, we will eventually see that this is the function e to the x. For now, we're kind of in the dark as to exactly what they converge to, but we do know that they converge on the entire real interval, this one at least. Let's look at another example. So for our next example, we'll look at n factorial over x to the n. So again, we're going to apply the ratio test. The limit as n goes to infinity of n plus 1 factorial x to the n plus 1 over n factorial x to the n, taking the absolute value of that. This ends up simplifying to be the absolute value of x times the limit as n goes to infinity of n plus 1, which is the absolute value of x times infinity, so it's just infinity for our limit. So for no values of x except when x is actually equal to, in this case, 0. So when I have 0 for my series, that series is obviously going to converge to the limit 0. So for no values of x except x equals 0, does this series converge? So aka divergence series. Except at the center. So we'll say that the radius is 0 and the interval is just not really an interval. It's just 0. Okay, let's look at another example. So we've seen one example where we had an infinite radius, one example where our series only converged at x equals 0, and then we'll take a look at another example. So for this one, we have x minus 2 to the power of n over n plus 1 times 3 to the n, and applying our ratio test, I have absolute value of x minus 2 to the n plus 1 over n plus 2 times 3 to the n plus 1 over x minus 2 to the n over n plus 1 times 3 to the n. And when I go ahead and simplify this ratio, I end up getting the limit as n goes to infinity of absolute value of x minus 2 to the n plus 1 over x minus 2 to the n times n plus 1 times 3 to the n over n plus 2 times 3 to the n plus 1. And we can simplify our x terms into x minus 2. And the 3 to the n's simplify into 3, but in the denominator. Which gives me the absolute value of x minus 2 getting factored out, taking the limit as n goes to infinity of n plus 1 over 3n plus 6. And that limit ends up being, factoring out the n, we have 1 plus 1 over n in the numerator and 3 plus 6 over n in the denominator. The n's reduced, so we're left with a third. So our limit reduces to 1/3 times x minus 2. Okay, so for our first instance, we have an actual finite limit. So remember that if our limit is less than 1, then our series converges. Okay, so if x minus 2 times 1/3 is less than 1, we have a convergent series. Okay, why are we not worrying about it being less than 0? Because absolute value, we can't have a negative. So I'm not worried about that. I'm only verifying where it's less than 1. So now I can solve this basic inequality. Remember, what we're solving for is we're trying to get an inequality that gives me my interval. So when I see x minus 2 times 1/3, if I multiply both sides by 3, I get, here's my interval coming up, x minus 2 less than 3. So what does that look like? Looks like your center is at 2. And then if you stay within 3 units in either direction, so we end up getting 3, 4, 5, and 3 units less than 2, gives me -1. My interval is -1 to 5, but what about the endpoints? So this is the first time we've had endpoints to check. So I need to manually plug in x equals -1 and x equals 5. So when I plug in x equals -1 to my series, I'm going to go all the way back, and I'm going to plug in here to my original series. So -1 goes in for x, and I end up getting the series -1 to the n over n plus 1. And I'm ranging from 0 to infinity. And when I take a look at what that ends up being, looks like we have an alternating series. And checking my alternating series test, I have b to the n over 1 n plus 1. I have 0 being less than or equal to 1 over n plus 1, and it's decreasing. That was a weird way to write it. Sorry for that. So we have b sub n plus 1 is definitely less than or equal to b sub n because our denominator is getting bigger, and 0 is a lower bound for all of them because our n's are positive. So we're satisfying the criteria for the alternating series test because as n goes to infinity, I have 0. So my criteria are satisfied for the alternating series test by the AST. Series converges. Okay, so by the alternating series test, our series converges. So -1 is included. And let's take a look at the other endpoints. For x equals 5, when I plug in x equals 5, I end up getting the series n equals 0 to infinity 1 over n plus 1, which if we actually look at what that is, it looks like, oh, we've never seen that before. But what is that? When I write out the terms, I get 1 plus 1/2 plus 1/3 plus 1/4. And do we recognize it? Well, this is equal to our good old-fashioned harmonic series. So our harmonic series was n equals 1 to infinity, 1 over n. So divergent. Now that we've seen the harmonic series so much, you guys can take it as a fact that we've proven that the harmonic series is divergent and just refer to that. Just let me know that you know that it's the harmonic series. Okay, so now we've established that the endpoints are not included. So the interval is -1 to 5. And we already figured out the radius was 3 units. Okay, something to just kind of look at on this example. I think it illustrates it really nicely. What we ended up showing, here's our center. How could we tell that 2 is our center? Look back at the original series, x minus 2 to the n. So 2 is expected to be the center. If you're getting a center that is not in your original series, you've done something horribly wrong computationally. So you should always expect to get your center here on the left-hand part. Okay, next, the radius says that you're convergent for all of these values interior to this interval. So anything inside here, it'll be convergent for. And we showed that the endpoints were not convergent. Okay, so this kind of covers all 3 possibilities that we can have for finding the interval and radius of convergence. Okay, let's take a look at why our power series are useful. So this is kind of what's motivating our study of these. So here's what makes power series useful. We can represent functions with power series, and we will learn in a future video what are the criteria, but just think of the fact that pretty much every function you've ever seen in your study of mathematics can be represented with a power series. So an awful lot of them. Not every function, obviously, it's very rare in math you get something that says, okay, everything can be this way. No, not everything, but quite a lot of functions can be modeled with a power series. So because of that fact, let's say our function is difficult for some reason. Our function is something that's really hard to work with, to integrate, blah, blah. Difficult to work with functions are going to become polynomials when we turn them into a power series, and then we can differentiate, integrate, and analyze. So we will not be doing that yet in this video, but in a future video, we will be going over how we can differentiate and integrate these power series and use them. So for example, just to kind of get a handle on how, like what's going on here. Let's say we had some function f, 1 over 1 minus x. What we'll be seeing is that 1 over 1 minus x can be represented with this power series, x to the n equals 0 to infinity. So we've taken a somewhat nasty function to work with, and we've turned it into a nice polynomial. And it's going to be an accurate comparison only on this interval -1 to 1. So if we look at what's happening with the pictures, here's my original curve here in blue, my original curve 1 over 1 minus x. And now as we look at the nth partial sums of this series, here's my second partial sum. See how close it is to that blue curve? It's super close. The fourth partial sum is even closer on this interval from -1 to 1. The sixth partial sum is getting even closer. So as we go further out, we're getting these curves that converge towards what the picture of 1 over 1 minus x looks like. And this is a useful tool for approximating values as well. There's a whole bunch of applications for why we might use power series. Spoiler alert, your calculator uses power series for virtually everything related to how it gives you decimal approximates. So it's using these power series to give you, like for instance, E up to a certain decimal place. This is the math that your calculator is programmed to do. Pretty cool. Okay. So let's use a power series to represent each of the following functions. These are kind of special functions that are vaguely related to, essentially to geometric series. So I'd like to point out the fact that this pattern here, 1 over 1 minus x, is that not incredibly remarkably similar to a over 1 minus r? So to me, that screams the fact that a is our first term, 1, and then our radius is then x. So if we put that in our formula, 1 over x to the n, that is the geometric series identity. Okay, and we need to have first term equal to 1, so I need to start at 0. Right? So just kind of outlining that again. My radius, I recognize this as a geometric series. Okay, so the geometric series says that you have your first term times your radius to the nth. And then if you need your first term to be 1, I couldn't start at n equals 1 because then my first term would be x. So I needed to make my index start at 0. So this is geometric series convergence formula in reverse that we just used. That's pretty cool. So without any work, this is a special function. I was able to convert it to a power series like that. Not all functions are going to be that easy, but for now we're going to look at the easy ones. Let's get a little more difficult. So let's say we wanted to express the function 1 over 1 plus x cubed as a power series. Again, I'm recognizing this as being very related to a geometric. If I rewrite this as 1 over 1 minus negative x cubed, then there is my r, and my first term is 1. So 1 times x, negative x cubed to the n. Starting my n at 0, going to infinity. I'm going to write this as negative 1 to the n times x to the 3n, just to make that notation a little bit more normal as to what we're used to looking at. And it looks like that's the final formula for it. And for another example, let's take a look at x squared over 4 minus x squared. Some algebra is going to need to be involved here. How can we rewrite this? So if I rewrite this as my a would be x squared times 1 minus r, I need to factor out 4. Okay, and then I get 1 minus x squared over 4 x squared. And then I'm going to put the 4. I don't want it in the denominator. That's going to become, that's part of the first term. So this is like x squared over 4 for my first term. And then this is like 1 minus x squared over 4. So my radius is x squared over 4. My first term is x squared minus 4. I get x squared over 4 to the n. And I'm ranging from n equals, I need to range from 0 to infinity to get my first term coming out. And then simplifying this, I can write this as x over 2 to the 2n if it's just a little bit more helpful. So if I want to put all the x's together, I would rewrite this as 1/4 x to the 2n plus 2. And then I guess it would be over 4 times 2 to the 2n. Really, these are all technically correct. It's just a matter of preference as to what is going to be most helpful for what. Okay, and then we were directed for the second part of these to find the interval of convergence. So remember, the interval of convergence, it's the case that for a geometric series, your radius has to be less than 1. So in each of these, we're going to go look at our geometric series and set the radius part to be less than 1. Okay, so setting our series less than 1, our interval of convergence is going to be, we're centered at 0. So if the radius is 1, then our interval would be -1 to 1. Okay, if we look at a number line, 0 is the center, 1 in each direction. And a geometric series converges on the open interval. That's a proven fact, so we don't have to check the endpoints. Okay, it's a known geometric series fact that it's only convergent on the open interval, so we're using that. We're not going to spin our wheels unnecessarily. Okay, let's try it on this one. So if my radius is -x cubed, setting my -x cubed less than 1. X cubed will be less than -1. That'll turn this negative. X cubed is less than 1. That's going to happen for -1 less than x less than 1. Because the cube root of 1 is just 1. So our interval is -1 to 1 again. And for the last example, the part that's getting raised to the power is x squared over 4. It needs to be less than 1. So we get x squared less than 4. X squared is always positive. Okay, so x squared will be less than 4 when -2 is less than x is less than 2. So square rooting both sides and then taking into account you have the positive and the negative is how we can get there. Okay, when it's equal to 1, we know that it's not convergent. So again, we don't include the endpoints for the interval. So there we go. So this first video is just exploring our basic, what is a power series? How do we determine the interval of convergence? In the next video, we're going to go over the properties of these power series, like how do we add them, multiply them, subtract them, what does it mean with convergence, and how do we integrate and differentiate? And that will be a very important tool for working with these power series. I'll see you then.